here so that we can watch these later when we're bored. All right, we're live. And so today's session is going to be all about aircraft systems. Let me share screen here. And there we go. Hey, but before I go, can you guys let me know what's the resolution look like on that screen share? Is it take up the screen or is it small?
I can make it as big or as small as I want.
Okay.
But I'm not a good test subject. I have a 34-inch monitor.
Got it. Chris, are you able to make the screen as big as you need?
Yes, I am.
Oh, okay, all right, and that's fine. On my system, it shows up really small. Okay, so we're gonna talk instrumentation systems. So cockpit instrumentation. We've already touched on some of this stuff through the sessions, like fuel gauges and stuff like that. But we're going to be looking at the three major instrumentation systems: the pitot-static system, number one; the gyro system, number two; and then there's usually an instrument or instruments that are hooked up to the aircraft's electrical system. So you'll see those three different systems. We'll learn those tonight. Of course, who can forget the magnetic compass, a device that every aircraft has to have. And then after we look over all the systems, we'll talk failure modes, because they all have inherent failure modes, and you have to be prepared for those when you're flying. Because depending on what the failure mode is or which instrument goes out, you'll have a certain protocol, or you'll know how to fly the airplane. Don't have the link. Emily's looking for. All right, let's 2 seconds, guys. I'm going to send Emily the link real quick. Apparently, I had a link snafu. Yeah. So here we go. Yeah. To your Gmail, yeah. All right. Okay. Back to it. Before we get going, though, I want to touch on something I did forget to talk about. My apologies last time we were together. Fuel grades. We talked fuel system, and we went over the different elements of the general aviation aircraft fuel system. I did not touch on fuel grades, though. It's a light topic. There's not much to it. But when you're out flying, you're going to see four different, I'll call it four major categories of fuel grades. You've got three octane gasolines, or aviation gasolines, and then you've got a kerosene jet fuel. So you've got an 80 octane avgas, 100 octane avgas, 100 octane avgas that contains low lead, so it's called 100 LL, and then jet fuel. And jet fuel comes in a couple different varieties. The most popular is called Jet A. Biggest difference between the octane gases and the jet fuel is kerosene, and the aviation gases are gasoline, similar to what you'd put in your vehicle. Now, when it comes to aircraft operation and understanding what the octanes do, you always want to use the correct octane for your aircraft engine, and it will be spelled out for you in the operating handbook. 90% of general aviation aircraft utilize 100 low lead, the blue, but some are certificated to use 100, 80, and even combinations of the three. I know the aircraft that I currently fly, you can use 100 low lead or 100. Always want to use the fuel grade that pertains to your aircraft to avoid elements that we talked about in the last class, such as pre-ignition. If you use a avgas that has a lower octane rating than your aircraft's certificated for, very high likelihood you will encounter pre-ignition, where the the cylinder fires in advance or out of cycle of its typical ignition stroke. The aviation gasolines are color coded with a dye, so that when you are inspecting the aircraft for flight and you take a fuel sample, you'll know what's in your fuel tank. Like I said, 90% of the time you'll take a fuel sample and it'll be a light blue color for 100 low lead. If it's 100, it'll be green, dyed green, and if it's 80, it'll be dyed red. Any questions on fuel grades?
Mm-mm.
Yep. All right, let's jump into tonight's material. I'm gonna dive right in. We've talked this. That's a Cessna 172 instrumentation panel. You can see it's got the typical what everybody calls 6-pack instrumentation arrangement here in the on the left side of the cockpit, and then this particular aircraft is outfitted with a GPS over here on the right. But this is a by today's standards very typical non-glass general aviation cockpit. So here's how we're gonna step through this. We're gonna talk about the systems. I'm gonna touch on system operation. We're gonna go through each particular instrument, one by one. We'll geek out a little bit on a few items just so that we can understand how things work, and then we'll talk failure modes and different let's call it nuances of the instruments that you'll be expected to know when you take your flight training. So the pitot-static system, this one you can actually, when you go to the airport, if you take a commercial flight, you'll very easily notice each aircraft out on the tarmac has a pitot tube. On commercial aircraft, they're typically located on the nose section, front area of the fuselage. On general aviation aircraft, it's typically located under the wing, on the underside of the wing. And it's this device right here, the pitot tube. Of course, all aircraft, including commercial airliners, have a static port as well. The principle of the pitot-static system is runs instruments under the principle of air pressure and pressure differential. And two instruments, the vertical speed indicator and the altimeter, which I'll explain in a couple slides, operate under the principle, strictly the principle of ambient pressure. And so, in essence, the only operating conditions those two instruments need are a static port, an open static port, free of obstruction, where static pressure, P sub S, can be introduced to the static port and through the static lines into the instruments. On the other side of the system, when we look at the airspeed indicator, it operates also on the principle of static pressure. However, it truly operates on the principle of pressure differential between ambient static pressure, the pressure that is outside the aircraft being introduced to the static port, and RAM air pressure, or as you'll see it called dynamic pressure, PD, through the pitot tube. Now, as the aircraft is flying through the air, at all times, static pressure will be acting on the static port. And in fact, static pressure will also be acting on a drain opening in the pitot tube. But more importantly, dynamic pressure will be acting on the pitot tube itself, inside the tube. As direct air enters the pitot tube, it creates a dynamic pressure. And the airspeed indicator uses that dynamic pressure compared to the static pressure acting on the static port and gives you an airspeed readout, a calibrated airspeed. As you can imagine, if the aircraft slows down, the dynamic pressure going into the tube will be less. So the airspeed indicator will indicate a lower airspeed. So at this point, from a high level, just understand that the pitot-static system operates principally on static pressure, the pressure, the ambient air pressure outside the aircraft, as well as ram air pressure or dynamic pressure introduced at the pitot tube. Just two other quick notes. Pitot-static systems generally have a pitot heater, so that if you're flying in inclement weather and your pitot tube freezes up, you will have a way to utilize your airspeed indicator by melting off the ice. We'll get into that in a little bit here when we talk failure modes. And second point, and we're going to use this throughout the session tonight, and we're going to actually use this probably throughout most of our follow-on sessions. So this is an important one. Standard atmosphere. When it comes to temperatures and pressures, the FAA and aircraft manufacturers recognize a standard temperature and a standard pressure for which they call standard atmosphere. And that the temperature is 59 degrees Fahrenheit, and the pressure is 29.92 inches of mercury. So if you had a mercury barometer sitting on your table that was graduated in inches, 29.92 inches is considered standard atmosphere. More or less, I really think that these numbers were picked because they're generally in the middle of typical ambient conditions that you will encounter. They're not on the high side nor on the low side. But as we move forward, when I mention the term standard atmosphere, if you hear the word, standard pressure or standard temperature, that's what this refers to. Standard temperature, 59 degrees Fahrenheit, 15 degrees Celsius. Standard pressure, 29.92 inches of mercury. All make sense?
Yep.
All right. All right, so let's dive into the airspeed indicators a little bit more. We talked a little bit about ram air pressure and its the instrument's ability to compare it to the static pressure. So the airspeed indicator is a sensitive differential pressure gauge, and essentially static air pressure is acting at all times on the airspeed indicator. So long as the static port on the aircraft is free of obstruction, and the aircraft is not moving, say it's on the ground, your airspeed indicator will be calibrated to show 0 miles per hour or 0 knots. As I mentioned, as the aircraft begins to move and begins to fly, the ram air pressure at the pitot tube overcomes the static pressure that's inside the instrument and begins to show a positive airspeed. It truly is no more complex than that. It's a pressure differential gauge that's calibrated to show you the speed, to translate pressure differential into aircraft speed. There are a handful of different kinds of airspeeds that I'm going to detail in I think 2 slides here, so I'm going to skip that for a minute. But while I have the gauge up on the screen, the colors actually have definitions and they have names for aircraft that are certificated for the kind of flying that we all do, and they're right there on the screen. The green range, which is typically where you'll always be flying, is your normal operating range. The yellow range is your caution range, and that red bar is your never exceed speed. So just really quickly, normal operating range is your typical operating range. It's self-defined. That's where you'll typically be operating the aircraft. The yellow range, caution range, is defined as the airspeed range for which you can operate the aircraft, but only in non-turbulence conditions or smooth conditions. If you are operating, say, at 200 in this case, it's miles per hour, 200 miles per hour on this airspeed gauge, and you begin to encounter even moderate turbulence, you will slow the aircraft down to below 180 miles per hour. And of course, the never exceed speed is a aircraft manufacturer defined airspeed for which you cannot exceed. Otherwise, you risk structural damage to the aircraft. The white bar is an interesting one. You'll see it in all kinds of aircraft, and that's the flap operating range of the aircraft that you're flying. Essentially, what it means is while you're within that white range, over here from say 67 miles per hour to 125, you may operate the flaps of the aircraft. Above that white bar, the aircraft is not certificated to be flown with the flaps operated. And of course, below the white bar, non-issue, because typically that's below stalling speed. All right. Now it doesn't end with just the ranges, and this is a slide that I think I'll probably take out of the presentation and put as a separate slide in the shared folder, because this one is something you'll always take with you. Have you guys heard, just in, I mean, for, being interested in aviation, have you heard of Vspeeds?
Yeah, like when you're watching that stuff, you usually hear like V1 rotate. I think V1 is where you're at the speed and distance on the runway where you can no longer stop. You have to take off.
That's right. Yeah, V1. I believe we don't use V1 in general aviation, but I think that's like takeoff safety speed or some such thing. Yeah.
Okay.
So yeah, exactly. There's somewhere in the neighborhood of like 20 or 30 Vspeeds. And from a, I'll call it basic level, general aviation level, I've put some here on the screen. And just real quick, go back to the airspeed indicator. Notice obviously the ranges here, the color ranges have a low or a minimum and a maximum, and green's got a minimum of 75 and a max of 180. So each of those points actually has a defined V-speed. For example, on the flap operating white bar, the minimum there on the airspeed indicator, and by the way, this goes for all aircraft. This is not only limited to general aviation aircraft. This is actually defined for all certificated aircraft. The minimum on the white bar is the stall speed and landing configuration. So gear extended, flaps full, and it's denoted VS0. And then in comparison, the minimum airspeed on the green arc is what's known as a stall speed in a specified configuration. And for 99% of the aircraft that we fly, specified configuration will be a clean configuration, meaning gear retracted if possible, flaps retracted, clean configuration. So when we go back to the airspeed indicator, you can see my minimum on the white arc here of call it 67 miles per hour is my VS0, which is stall speed in landing configuration, and green is my stall speed in a non-landing or a clean configuration. And of course, the principle here is the fact that as you extend your flaps, your stall speed goes down. Generate more lift, your stall speed goes down. So you can see that each of these points has a different V-speed. Maybe it's obvious now that we've talked about it, but the high or the maximum on the white arc is the maximum flap extend speed, for which beyond that speed you cannot extend the flaps. Now there's airspeeds or there's Vspeeds rather, that are not visually defined on the airspeed indicator. I've put 3 of them down here. There are probably 20 or 25 others, but these 3 are the ones that you'll use all the time, especially as you start your training. Maneuvering speed, best angle of climb, and best rate of climb speed. Anybody want to venture a quick guess on best angle of climb, best rate of climb? What those are?
Where you have the right efficiency, where I'm trying to remember the name of that graph from the first class.
Oh, the lift versus drag.
Yeah.
Yeah, actually, I do believe there is a relationship to that particular chart. We have to pull it out. Maybe we'll look at it when we finish up here. But yeah, you're thinking along the right lines, right? It's the speeds for which your aircraft will attain a certain performance standard in a given distance or time. So best angle of climb, for example, Vx, and I'll highlight it. Oops. Right here, Vx, is the speed for which your aircraft will climb the most altitude in a given distance. And conversely, Vy, or best rate of climb, is the speed at which your aircraft will climb the most altitude in a given time. So that's why they call it best rate. It's how quickly can I get the highest altitude in a given amount of time. These 2 airspeeds are important because they're used for takeoff performance considerations, which we'll get to in a future session. If you're about to depart an airport that is on the hairy edge of your aircraft's takeoff distance performance standards, and there's, say, obstacles, trees, power lines at the end of the runway, you're going to be very focused on getting the aircraft to the highest altitude that you can in either the shortest amount of time or the shortest distance. Typically, when we're talking takeoff and obstacles, it's distance. So Vx becomes very important in those kind of performance calculations. And the Vspeeds are calculated for each individual aircraft. So Vx, Vy, and all these other Vspeeds have definite defined values for each aircraft. Maneuvering speed, skip that one. Maneuvering speed is a speed at which the aircraft can be operated and withstand what they call a high stress or a gust. And you might say, well, didn't we just talk about that? Isn't that kind of the yellow area? Well, it is, but the reason maneuvering speed is a kind of a separate airspeed is very, often, especially us, we're involved in flight training. You're going to be going up and performing maneuvers. It's stalls, slow flight, steep turns. And the aircraft manufacturers have defined this maneuvering speed such that you can put stresses on the airframe by performing those maneuvers, and still know that your aircraft's not going to fall apart if it encounters turbulence or a strong wind gust or what have you. All right, so these are Vspeeds. I'm going to make a note here. I'll send out a list of all the FAA-defined Vspeeds. It's quite an extensive list. You guys can look at that. Any questions on Vspeeds while we're on it?
Will the exam typically cover most of them, or is it just sort of the key ones you've identified here?
Key ones. These, and I'll go back and look, but these will definitely be covered on your written test and definitely on your practical flight test.
Okay.
Yep. And then, like I said, if you're talking to an examiner or, your flight instructor, they're going to want to know that you understand how to operate around these Vspeeds. For instance, examiner might pose the question about the short takeoff. Hey, taking off from a short runway and you got 30-foot trees at the end. Talk to me about your takeoff. What speed are you going to use? And you would say, well, I want to gain the most altitude in the shortest distance, so I'm probably use VX. Same as with the turbulence discussion. Someone might ask you, well, you're flying along at in the caution range, and you start to experience moderate turbulence. What's the first thing that you do? And you'll say, well, I'm probably slow my airspeed down to the normal operating range because the aircraft has been certificated to operate in that range in moderate turbulence or what have you. Make sense?
Mm-hmm.
All right. So the airspeed indicator is kind of just one, call it element or one set of definitions where you have a bunch of Vspeeds. There's also a whole list of airspeed types, for which the airspeed indicator is just one of those types. And you might have heard some of these definitions in other contexts before, but you've got true airspeed, indicated airspeed, ground speed, and you've got this thing called calibrated airspeed. And they all are different. Very infrequently will any of these values be the same. But we're gonna go through them one by one here. So indicated airspeed, probably the simplest to understand, is simply what the gauge says. So it really is just simply what the gauge tells you the airspeed is. That is indicated airspeed. If air traffic control asks you what your indicated airspeed is, you tell them whatever's on the gauge. As opposed to true airspeed. True airspeed is the airspeed for which the aircraft is moving in the air mass that it's currently located in. So right away, you're kind of like, that's pretty confusing, right? Because the airspeed indicator should probably kind of like sync up with what your true airspeed is, right? Can anybody tell me, does anybody know why those two might not be the same?
Which two? True airspeed and what?
True airspeed and indicated? Guesses are okay.
I'm thinking.
Chris, Emily, any venture a guess?
The wind have anything to do with it?
Say that again.
The headwind?
Wind does not have anything to do with the difference between true and indicated. It does affect the difference between true and ground speed.
Okay.
Is it because the pressures change as you're at different altitudes, so the PS and the PDs aren't always exactly correct?
Yeah, that's spot on. So that's exactly right. Your airspeed indicator is calibrated at sea level, at 0 feet, and in a standard atmosphere condition. So they calibrate the airspeed indicator at 59 degrees Fahrenheit and 0 feet, what's called absolute altitude. As you go up in altitude, obviously your air gets less dense, the air pressure goes down, and typically as you go up in altitude, it gets your air temperature goes down. So the difference between what's showing on your gauge, your indicated, and how fast your aircraft's actually going is going to be different. So true airspeed, the way you can remember that, true airspeed is always affected by the ambient conditions. And your indicated, your airspeed indicator is is because of its calibration point. It's calibrated at sea level, standard temperature, standard atmosphere. It's always only going to be 100% accurate at standard atmosphere. And then as Alan mentioned correctly, your ground speed is going to be your true airspeed corrected for wind. So if I'm flying along at 100 miles per hour, but I've got a 50-mile-an-hour headwind, my true airspeed will be 100 miles an hour because it is the speed for which I am traveling through the relative air mass. However, over the ground, it's going to be much slower. It's going to be only 50 miles per hour in that example.
So I want to go back to the true airspeed, indicated airspeed. So the reason I didn't originally go with pressure is I just figured the gauge would have been designed to handle those pressure differentials, given that the very nature of flight is to put you in different pressure tiers as you change altitude. Does it not work in connection with the altimeter to understand altitude and therefore relative pressure to the external part of the plane?
No, it does not. The altimeter and the vertical speed indicator are the only instruments that actually utilize the pressure difference to give you a like an altitude difference. The airspeed indicator does not take that into account.
See, that's where I got confused. I was for sure that the gauge, like, so what amount of inaccuracy are you introducing as you change altitude? I mean, is it nominal difference where we're talking a few miles per hour between true and indicated, or are we talking much more?
It's, I mean, I'll call it substantial. I mean, it's substantial enough to pay attention to. It's one of the reasons why, as a pilot, you're always very keen on trying to fly at a higher altitude, so that you can get a higher true airspeed. So if I were to maybe pull some numbers out of the air, if I'm traveling at, say, 150 miles per hour on the ground, and let's just say for sake of argument, I'm at sea level. So my true airspeed and my indicated airspeed are going to be relatively the same at 150 miles an hour. And I go up to 10,000 feet. It's very possible that the indicated airspeed is going to go down. If I hold 150 miles per hour true airspeed, the indicated will go down somewhere in the neighborhood of 130 or 120.
Got it.
Yeah, so it's significant. It's worth paying attention to, so to speak.
Okay.
Yep. Now, from here's what I will say. From a flight planning perspective, you will you'll never consider indicated airspeed from a flight planning perspective, because the only thing not the only thing, but the major element we do care about when we're doing our flight planning is, how long it takes us to get from point A to point B. And of course, because wind comes into play there, we're going to be thinking about our ground speed.
Okay.
Yep. More and we'll talk more on that during the flight planning. Just two other things actually. True airspeed, because to Alan, to your point that you just made a second ago, the aircraft's manufactured, and the aircraft, the builder of the aircraft, the designer of the aircraft isn't stupid, right? They know that this thing is going to be flying from sea level up to 15,000 feet and everywhere in between. So when the aircraft manufacturer designs and certificates an aircraft, all of the testing and the data and the performance standards that you get to see in the operating handbook are based on true airspeed, because that is the aircraft's actual speed in the air, and they want the design of the aircraft and the performance, published performance, to be indicative of how the aircraft, or how fast the aircraft actually flies in the actual air mass. So typically you just won't handle indicated airspeed that much. You'll know that it's on your gauge, and if someone asks you what's your indicated airspeed, you'll know where to look. But flight planning and performance purposes, you're typically looking at true airspeed and of course ground speed. One more point, calibrated airspeed. This airspeed is always forgotten. When I was going through my training and then getting subsequent certificates, you always come back and have to remind yourself what calibrated airspeed is. So the airspeed indicator is a calibrated instrument, meaning just like a weight scale or a pair of calipers. It's a calibrated instrument. It is susceptible to calibration error. Your calibrated airspeed is the indicated airspeed corrected for any calibration, installation, or position errors. Installation errors being any sort of pressure anomalies in the pitot-static system, anything that might come up during installation. Position error is, let me go back a few slides. Position error is how the airspeed indicator, its error potential based on the pitot tube's alignment with the wind. So as you might imagine, if you're in a significant nose up attitude, the oncoming wind is not hitting the pitot tube at exactly a perpendicular, exactly head on. So the calibration error takes into account the fact that your relative wind to the pitot tube might be at an angle. And calibration airspeed is not indicated anywhere. Again, you will, hate to say it, but you'll probably never use calibrated airspeed, but it is one of the airspeeds that the FAA expects you to understand what that is and be able to define it. Okay, anything, before we leave airspeed, any other questions on the airspeed material?
Will
Okay.
true airspeed always be higher than indicated airspeed?
So yeah, I would say commonsensically 90% of the instances where you're going from I'll call it an air mass of high density to low density, when you're increasing altitude, that will be the case. What I will say though is it just depends. If, let's say you're on, and I'll just use an example. Let's say you're on final approach and maybe 2 or 3 miles from the runway, and you encounter wind shear, a significant gust. Now, your aircraft's going to react to that. Of course, your true airspeed is going to change because, like we said, the true airspeed is what is your aircraft's actual speed relative to the air mass. But instantaneously, your indicated airspeed is going to be higher from that wind gust. Why? Because a straight-on headwind wind gust is going to hit your pitot tube and it's going to make your airspeed indicator jump up to a high value. And it'll do that much quicker than your aircraft actually changes true airspeed. That's, that's one example I can think of. But yeah, 90% of the time, your aircraft's going to be traveling faster through the air than your airspeed indicator is going to be indicating. All right. All right, the altimeter. So as I mentioned before, go back here. Of the 3 instruments that we're talking about on the pitot-static system, airspeed indicator, vertical speed indicator, and altimeter, the altimeter and the vertical speed indicator only care about static pressure. They do not deal with the dynamic pressure portion of the system. So your static port, which provides your static pressure, will affect the readings on your altimeter. And your altimeter is really nothing but a fancy barometer. It's exactly what it is. It's a barometer. It utilizes air pressure to give you a reading on a dial. And the reading that it gives is your altitude position above whatever pressure level that you have set on the instrument. Now, the altimeter has what's called a Colesman's window over here, for which you can set to set the altimeter to a pressure level. And the altimeter is going to give you the altitude above the pressure level that you set in that window. If you remember a few slides ago, I mentioned standard pressure in a standard atmosphere is 29.92 inches of mercury. And so you can see this particular altimeter is set just a touch below that at 29.86 or 87 inches. So there's a lot of misconception out there initially. Folks think that an altimeter gives you the altitude of the aircraft above the ground, but that's incorrect. It actually gives you the altitude of the aircraft above a pressure level, which you set in that window. Now, in practice, when you're flying the aircraft and doing your cross-country flights, in practice, you will always set that pressure window to the most accurate barometer setting that you can get, which is typically, that's typically the airport you're departing from, or as you're going to your destination, it may be a pressure setting from an airport en route. And what that'll do when you set that pressure setting that you get from the airport, it's going to give you your altitude above that pressure setting, which is sea level. It's going to give you your altitude above sea level. And so if I am at, say, Dallas Love Field, which has a field elevation of about 600 feet, if I set their barometric pressure in my Colesman's window, my altimeter should correctly read 600 feet, which is field elevation. Now, there is another type of altitude called pressure altitude, for which you don't use the field elevation, and I'm gonna get into that in a couple slides here after we talk about a little bit about how the instrument works. Does that make sense in general? How the altimeter gives you your altitude above a pressure level, not necessarily above the ground level? Does that make sense?
Yeah.
Okay. Chris, Emily, is that pretty clear?
I think so.
Yeah.
Okay. So the altimeter. Now, this was always kind of funny when I was going through my training, because I never really paid attention really how the gauges physically worked, and then came to my my practical test with an FAA examiner, and he asked me how the forget which gauge it was. It was one of the gyro gauges, but he wanted me to explain and potentially draw out how the gauge worked. And so ever since then, I've taken it pretty, somewhat seriously. When you're flying the airplane, of course, you only really care about what it's telling you for the most part. But altimeter is, like I said, it's a barometer. And what is a barometer? Well, it's a set of stacked what's called aneroid wafers. And they expand and contract under different pressures. Of course, if you've got your Colesman's window set to a particular pressure, that'll preset the wafers, and then any change in pressure from that setting will cause the instrument to turn. So, for example, as you increase altitude, and the pressure differential between what you have set in the window versus what the static port is telling the altimeter, as it goes down, the wafers expand. The expansion of the wafers causes, through the gear mechanism, causes the altimeter to indicate an increase. It causes it to go up. And it's really no more complex than that. It's a fancy barometer. It's a fancy, expensive barometer. And the as you guys have indicated with the airspeed indicator, the fancy, expensive barometer is also very much so susceptible to ambient condition changes, pressure and temperature. And there's a couple monikers out there that people have come up with just to ease the understanding. But on the next slide, I'm going to kind of show graphically how a change in pressure or a change in temperature could potentially affect how the gauge reads. And for now, just know that it does affect it, and people have come up with a couple of these monikers, going from high to low, meaning pressure. Look out below, meaning if you're flying from an area of high to low pressure, and you don't take that into account with your altimeter, setting your altimeter, you could run into the ground. Your altimeter could be giving you a false reading, thinking you're higher than you actually are. And then there's from hot to cold, look out below. So if you're flying from an area, higher temperatures to lower temperatures, a similar issue. Your altimeter may be telling you you're higher than you actually are. So graphically speaking, and then I also put some numbers to this too, because it kind of helps to understand how much it affects. Here's a example where the top aircraft's flying from standard atmosphere, 29.902 inches mercury, to a location where the pressure is 29.42 inches mercury. And let's say the pilot at the beginning of his flight correctly set the altimeter so that his indicated altitude was showing 1,000 feet on the altimeter, and his absolute altitude, which is his altitude above sea level, was truly 1,000 feet. Everything's good. If he or she forgets to set the altimeter when they get to their low pressure destination, for these particular barometric pressures, his altimeter may indicate 1,000 feet, but he's only going to be 500 feet above sea level. So you get a feel for the magnitude. Such a small change in barometric pressure, 29092 to 29042, can cause such a discrepancy in true altitude versus what you see on the gauge. And when you try to think of it scientifically, it kind of makes sense, right? You're flying along, maintaining an altitude that either you're told to maintain or you're planning to maintain. All the while, the pressure is getting lower and lower at your destination. Your altimeter is just a barometer. It sees that decrease in pressure as an increase in altitude. So as you're flying along and your altimeter is quote unquote increasing, well, you're descending to hold that 1,000 feet. So what's the result? The result is you end up at a lower, true or real altitude. Your altimeter doesn't think so, but your aircraft's actually lower than your altimeter says. Does that make sense to everybody? The pressure differential, the altimeter setting, and the absolute altitude.
Mm-hmm.
Yep. Same goes for temperature. There's that equation. You guys remember the ideal gas law equation? Pressure volume equals constant temperature. So it's going to do the same thing as you go from a area of higher temperature to an area of lower temperature. All things considered equal, your pressure is going to go down. Your air pressure is going to decrease. And so it's really not quite as crazy, or I'll call it the magnitude of change isn't as much as the pressure is. But you can see in the example I gave there, 10 degrees Celsius, which is, I don't know, somewhere in the neighborhood of 40 degrees Fahrenheit maybe. You've got absolute and indicated 1,000. And then as you go down to negative 10 Celsius, which maybe 25 degrees Fahrenheit, you lose 100 feet. Not as crazy as the pressure difference, but when you're if you're flying a commercial airliner and you're on a instrument approach that takes you down to minimum altitude, 100 feet can really make a huge difference. So just things to keep in mind. And again, people love to use the phrases, going from high to low, look out below, going from hot to cold, look out below, meaning look out below, you're going to hit the ground. Similar to airspeeds, there are a set of defined altitudes for which you're going to want to become extremely familiar with definition-wise. Indicated altitude, similar to indicated airspeed, is simply what the gauge is telling you. You look at the gauge, it says 900 feet, your indicated altitude is 900 feet. True altitude is the vertical distance of your aircraft above sea level. And in aviation, we utilize the acronym MSL, Mike Sierra Lima, to stand for mean sea level. You'll hear when we watch our videos, and if you're listening to air traffic control, you'll hear that phrase all the time: MSL, MSL, MSL. It means the aircraft's altitude above sea level. And if you've got your altimeter set correctly, your true altitude and your indicated altitude will be one and the same. Absolute altitude is the vertical distance of the aircraft above the terrain. Again, another acronym, AGL.
Adam, we can't hear you.
Oh no. Test.
Yep.
That's better.
Oh no, where did you lose me? Back at airspeed?
Right as you're about to go into absolute altitude.
Okay. Got it. All right, so we didn't lose too much. Absolute altitude is
Your
the
screen, though.
What's that?
We've lost your screen.
Okay. I see that. Here we go. Okay. Still, I'm not getting the screen share. Can you see the screen?
No.
All right.
All I see is your avatar.
Yeah, that's all I see too. Just a second here.
Okay.
All right. All right, let's see. Well. Well, let's do this. We won't fumble around too much with technology. I'll just send you guys the pitch and we can kind of go through it so we don't lose too much time. You guys okay with that?
Yeah.
All right. Let me send this out here. Suppose I could try to restart this thing.
That could work too.
Yeah. Why don't let's do that. Let me kill it and we'll rejoin. So exit and then re-hit the link.
Okay. Don't forget to rebroadcast.
Yep, you bet.